Now, we just did we just did free radical substitutions on Friday. Now, that was a long mechanism with a lot of possible steps, and some even of the ones that you had to know, there are other ones that probably did happen anyway, and just wouldn't have any real effect. Like a chlorine free radical banging into a chlorine molecule and forming another chlorine free radical and another chlorine molecule. Obviously that happens, but it doesn't really do anything. And that's in addition to all the steps I showed you. Well, this was nowhere near as long. Electrophilic addition is going to only have 2 steps. But I need to explain them because it helps for us to explain Markov-Nikov's rule. Okay? So it's going to explain some addition reactions. Remember how I told you one of the reasons we do learn about mechanisms is it actually makes, it's not just to make things more complicated, it's actually to make things a little bit more easy to understand. Why? Because many different addition reactions actually go by this mechanism. Not just one reaction is explained by this, but multiple ones. So, like, for example, if I was making an alcohol and adding water to an alkene, that would be an electrophilic addition. So would adding HBr or HCl or HF or HI. Same thing. They would all be explained by electrophilic addition. And there's others too besides that. All right? Now, you're going to be working the lights today a lot, Olivia. I want to show you, I'm going to start off with an overall video clip of what's going to happen overall, okay, the different steps, and we'll talk about it. I'm also going to pause it at that point to tell you, because there's going to be some new terminology in this. Don't worry, I'm going to give you all the things that he's saying in this little video clip I'm going to explain for you in notes. But I want to show it to you first, and then I'll break it down for you. Okay, hit that light. Great music, too.
Electrophilic addition involves 2 reactants. An alkene, whose double bond is rich in electrons and is thus nucleophilic. And an electrophile that will attack pi bond electrons in the alkene double bond. We'll use hydrogen bromide as an example. Ultimately, they will react to form an alkane. This reaction takes place in 2 steps and is exergonic overall. So what are the mechanisms? One reactant is a potential electrophile. Because the bromine atom is electronegative and attracts electrons, it causes a partial positive charge on the hydrogen atom to which it is bonded. The hydrogen is thus electrophilic. Remember that a double bond contains 1 sigma bond and a weaker pi bond. Weaker because their orbitals do not overlap.
I'm going to pause it right there for a second. Already you've heard electrophilic, electrophile, nucleophile, and you're going to hear some other words that either sigma bond, pi bond. All right, don't worry, I'm going to explain most of these. But the one I'm not going to explain is what he's showing here. And I am going to do this in the future. Right before the AP exam, I'm going to go over some Lewis structures again with you and bonding. And how do we write them correctly? Because up till now, you've only done very, very basic Lewis structures, very basic bonds. We know what double bonds are, but you really don't know what the bonds look like, the sigma bond, the pi bond. I'm going to talk about that. I'm going to do some of that stuff with you in the future. For now, all that's important that you know, okay, is that the double bond, this is an area where there's a lot of electron density. There's a lot of negative charge there. Because remember, they're sharing 2 pairs of electrons. Meanwhile, this HBr, as he was showing you, actually is what we're going to call an electrophile, the one part of it's going to become, because bromine is going to be pulling those electrons closer to him, which means hydrogen will be slightly positive. That slight positive here is going to be attracted to the negative electrons in here, as you'll see with the rest of this. But I know a lot of those words sound new. I'm going to define most of them for you and talk about them as we go along. But the one thing I won't is just the sigma bonds, the pi bonds. We are going to talk about that, just not in this chapter.
These pi electrons are thus attracted to the partially positive hydrogen atom in the halide molecule and are able to form a stronger sigma bond. Because an electron has been removed from the adjacent carbon atom, the carbon atom becomes positively charged. This is called a carbocation. Meanwhile, this hydrogen has 1 too many bonds, and a pair of electrons transfers to the bromine atom to form a bromide ion. This is the first and slowest step of the electrophilic addition reaction. This step gives rise to a carbocation intermediate as well as a bromide anion. The bromide ion is now a suitable electron donor for the carbocation. The molecule is neutralized, and an alkane results as the final product. This concludes the last and faster step of the reaction.
Okay. Now let me break that down for you. Hit that like for me. Let me break all that down for you. Okay? You already have this much so far. I'm going to break it down and show you the mechanism, and the mechanism is 2 steps, and I'm going to do it. You've just seen that happen as stick figures. I'm going to show it to you again and write words underneath it and explain it. And then I'm going to show you in one more video animation actually of both steps individually. So at the end of this, I think it'll all make sense. All right? First of all, the mechanism. Okay? The first step looks like this, and I think you have this on your notes already. It looks like this. Okay? Same kind of what he was showing you there. Although he had just H's on all these, he was just using ethene, for example. We can have any amount of carbons coming off of there or whatever, as long as there's a double bond. And then we have HX. X could be, he used bromine, but it could be chlorine, fluorine, OH. It could be other things. Anything that X is going to be an electronegative group or element that's pulling electrons closer to him. Now, we've seen that before. All right? Since those electrons are being pulled this way, okay, they're going to be slight negative. That, by the way, the abbreviation for a negative charge, slight partial charge. It's a partial positive, partial negative. You may see that written in the AP exam. All right, that just means there's a partial separation of charge, slightly positive on this side, slightly negative on that side. All right. Either way, this guy's going to be slight negative, slight positive. This positive side is going to be attracted to these negative electrons. Remember, we're sharing 2 pairs of electrons there. So it'll be very negative there. He's going to be attracted to that, and he will pull that H off, and he will attach right there. Now, when he does that, what happens is this guy's going to have an excess positive charge because H did not bring that electron with him. He left it here. X now looks like this. He's got a negative charge, a full negative charge now once that H leaves. He's an ion. And this guy's also an ion, but he's called a crazy name. He's called Carbonium Ion, or carbocation. This guy over here, the guy that was attracted to the negative stuff, was called an electrophile, or electrophilic group. I've often asked you to think about the words and what they mean. Okay? Like, break it down. The prefixes, the suffixes. Electrophile. Where have we seen, and I've used this before, I know I have, in both Chem 1 and this year, I think. Phile. What does it mean? You heard words like, what does it mean? Yeah, you've heard it, pedophile. It means attracted to, right? A pedophile, it means loving, basically. Philadelphia is a city of brotherly love, okay? Remember in biology, hydrophilic versus hydrophobic. So the opposite of philic is phobic. And we know what phobic means, right? We know phobias, right? Okay, so electrophiles are guys who love electrons. The electrophile is the hydrogen part of this HX who's attracted to those electrons, all right? The carbonium ion that's formed, this is the crazy part here. This is going to seem like the opposite of what I told you, but I want you to listen to this. We're going to find that this positive charge here can be much more easily dispersed if there are other groups around him, other carbons around him, other alkyl groups around him. So I want that to form on the carbon that is of the highest like tertiary versus secondary versus primary. That's why it forms on that. Okay. So this H actually adds to the guy who is, for example, given a choice of primary or secondary. Where's the H going to add in this case? Believe it or not, the H adds here because that forms a carbonium ion on this high carbon, and then the bromine's going to come in and add to there. Now, all of that I've just talked about, I want to explain to you in words underneath all this, okay? So let's write some of this stuff down. First things first. Double bonds are regions of high electron density. There are a lot of electrons being shared there, a lot of negative charge. There's also a sigma and a pi bond. We'll talk about that later. But all you care about right now is that there are negatively charged, it's a negatively charged area. Now, to complete that same sentence here, those negative electrons are going to attract electrophilic groups, guys who have slight positive charges on them. They attract positive atoms or groups called electrophiles. And I want you to make sure you highlight or underline these new words like electrophile.
It is on the second line.
Nope. It's the same sentence. I even said that. So to complete this sentence, it's not part of the next dash.
We don't have it.
Yes, you do. You fit two lines in there. You can do that. And if you don't, so what? There really are. It's not a big deal. Who cares? There's enough room to show it wherever you need to. Doesn't make any difference how many dashes there are. Now here's another new word: the carbonium ion or the carbocation. That's another new word. Make sure you highlight or underline that. I guess there are only, I don't know how many more dashes there are here. I think there are 2 more, but I'm not positive. Doesn't really matter. Now, the carbonium ion is this whole alkyl group with a positive charge. However big that alkane is. All right, so that's your first step. And the last thing I want to say about that step is this. That positive charge right here will form on the more substituted carbon. Carbon has more carbons around it. Okay, that's the last thing you want to say here. And I also want to kind of review this with you. Before I say the last sentence. There's a statement on there. Because I was surprised that people did not know what tertiary, secondary, and primary carbons were on the test we took, at the end of the last unit. Remember, at the end of the last unit, I split into 2 tests. I had the objective test, and on that objective test, I drew a compound. Okay, most of it was A, B, C answers. It was matching multiple choice about the different functional groups, R, C double bond O, R, OH, R, whatever. And you had to tell it was an ester or carboxylic acid or an aldehyde. Well, I also did something like this. I also drew some. I don't want you to draw this now, but we also did this. Do not draw this. And I asked you I think that's the exact same compound I drew for you. I asked you in that compound to identify, circle all the primary, box all the secondary, whatever all the tertiary ones in that. And I thought that was a gift. I thought everybody's going to get that right. But I was surprised to find that a good 10 to 15, maybe even 20% if you did not get all of that right. You certainly should know which ones are primary, secondary, or tertiary out of this. What is this guy right here? What is he? Primary. Are there other primaries on there? Sure. Right here, here, and here are all primary, aren't they? How about secondaries? Is this a secondary? Is that? Yes. And this guy? Yes. Which means these 2 guys must be what? Tertiary. Okay. And you know that, here's why. Secondary ones, like I have boxed here and here, are bound to 2 other carbons. Secondary 2. Primaries only bound to 1 other carbon. Tertiaries bound to 1, 2, 3. Can you have quaternary? Yeah, but if I have a quaternary carbon, I can't have a double bond between him and somebody else. So it really doesn't make a difference. I'm not going to have anybody add on to a quaternary carbon. Right? So basically, primary, secondary, and tertiary are the ones we care about. And you want to form that positive charge on the tertiary rather than the secondary, rather than the primary. All right, given a choice. Remember, choices are not unlimited. If I have my thing here, my double bond is here, my choice isn't going to be over here. He can't go over there, right? You're not going to be able to make the positive charge there. It's going to be between those 2 guys. Okay. Now, of course, as you probably realize, because the next step is going to form this guy right here. This guy right here is going to become an ion afterwards, and we know he's an ion. Those 2 guys are going to get together like that. It's going to happen really fast. Okay? This is a slow step. Now you say, well, why am I bothering to point that out to you? Believe me, Which step is the slow step is really important when it comes to something called kinetics, the mechanism, being able to predict which guys actually contribute to how fast the reaction happens. And this is the slow step, okay? And you want to write that down. This is the slow step, or the rate determining step. It turns out the rate of this reaction is determined solely by this one step. I will make this more clear tomorrow, although I still won't make it as clear as it's going to be when we get to the chapter on kinetics, and I do a demonstration for you, and we start working with rate determining steps in the mechanisms. So when we get to kinetics, I will come back to this and actually the SN1 and SN2 reactions, and I will point them out to you how it's weird, but only one of these two steps. In some cases, I can add guys together in a reaction, and like A plus B yields C. This is going to sound strange to you, but it will make a little bit more sense tomorrow, and a lot more sense in the kinetics chapter. A plus B yields C. You'd say, well, okay, if I want to make that reaction go faster, I can increase the concentration of A, and that'll make it go faster. Or I can increase the concentration of B, or both of them. But in some cases, that's just not the case. I can double the concentration of A, triple the concentration of A, quadruple it, and it would make no difference to the reaction rate. You say, how can that be? It has to do with if he's involved in the slow step. If only B is involved in that rate determining step, he's the only guy that determines the rate of the reaction. The other guy just has to be there. Because the difference between the speeds is often on the order of thousands of times faster or slower, not just like a little bit faster or slower. That won't make complete sense. A little bit better tomorrow when I talk about it. Way better when we have a whole chapter on it, on kinetics. You have to kind of like wait for that. All right, so there's your first step. There's your slow step. I'm attaching this H to there, making this carbonium ion. The next step is going to be the easy step. Turn that light off for a second. I'll just show you a video representation now of the molecules coming together. This only takes a second. Watch. Okay, this is exactly what we're talking about. This H, the Br, slight negative here, slight positive there, attracted to those negatives, attaches to one of the two. Notice which one he decided to attach to. Did you notice this? He had a choice between where he's going to attach, right? He attached to the guy with fewer carbons, so that the charge will form on the guy with more carbons. You see what I'm saying? So that's why the first step actually is kind of backwards from what we memorize about Markov-Nikols's rule. Markov-Nikols's rule, I said, things tend to go on the more substituted carbons. They will. The hydrogens tend to go on the less substituted carbons. The hydrogen is the first thing to attach. That's why he goes here, makes the carbonium ion there, the carbocation there, and now that bromine in the next part will attach there. All right, so let's look at that second step here. Oh, and by the way, you have the same, you get the light back on. You have this exact same picture there. It's just another way, another little description of what's going on. Here's your negative electron clouds from the double bond. This guy is more electronegative than him. Notice that partial positive, partial negative. So you got a partial positive here. You got a partial negative there. They're attracting, okay? X versus Y. That X is probably an H, a hydrogen. The hydrogen attaches here first, and then the other guy will attach to the second step. So let's do that second step. Here's your step 2. I already have it drawn for you. This is really fast. You've got two unstable guys, two very reactive particles, a carbonium ion and a halide ion or an OH ion, whatever. Very reactive. They're going to get together very quickly, attach themselves together, and form the actual product. So in the second step, nucleophile. That guy's called a nucleophile. You're going to want to highlight him. That's another new word, nucleophile. The nucleophile attacks the carbocation. And by the way, I've been using the terms interchangeably, carbonium ion, carbocation, okay? Depending on what kind of professor you get, if he's older or younger, he may use one or the other or both terms. But they basically mean a carbon compound that has an ion formed on him. Now, nucleophile. Who do you think he's attracted to? Well, obviously attracted to nucleuses. Well, what charges do nucleuses have? What charge does the nucleus have? Positive. That's why the nucleophile, the guy who's attracted to a positive thing, would be, in this case, that guy, right? Right? Okay. Guess. I guess. This step occurs much faster than the first step. And because of that, it has no effect on the overall rate of the reaction. And that, in this case, isn't as big of a deal as it's going to be when determining SN1 versus SN2 mechanisms. That's why I'm saving this a little bit for tomorrow. It's going to be a much bigger deal tomorrow that the second guy is completely in the slow step, in the faster step, and isn't really involved in the slow step at all, means something. And we'll talk about that tomorrow a little bit more, although I've already hinted at it today. So that first step, which is really slow, this guy, as soon as that carbonium ion is formed, this form, they, bam, get right together. I mean, it doesn't take any time at all. This could happen thousands of times faster than the first step. Okay. All right. Now, what kind of question? I'm going to put the summary up here. Lift that light off again. Here's the second step real quick. The bromine ion attaches to the carbonium ion, and you get your product. Notice the bromine is on the more substituted carbon, as you'd expect. But I wanted to show you, light on again. All right, I want to show you what kind of questions I could ask you about this. What are the questions I could ask you? I'm going to give you 2 worksheets today. Only one of them you're going to collect. And you're going to have some help with the computers back there. You're going to use those. Okay, not Beaker actually this time. You are going to use Beaker on Thursday one more time. Last time, we're going to use Beaker. But if I asked you, what kind of questions could I ask you about this mechanism? I could say to circle the electrophile in this reaction. Who would you be circling as the electrophile? So everybody, I don't know if I heard everybody say this, but I've heard several people say, it looked up to me in life, I'd be circling H. Oops, sorry. I'd be circling H. Right? And I would. Not HX, just H. The H is the part that's slightly positive, and therefore is attracted to these negative electrons over here. Got it? Oh, make it darker. See? You can cover it all up. That's cool. All right. What if I said to circle the carbocation? What would you circle? I would circle this whole thing. A lot of people will just circle this. That's just the positive charge. The whole guy is a carbonium ion. Okay? So you would circle that. What if I said to circle the nucleophile? I'd be circling the X. Where would I circle them? Here or here? Down here, because that's where he's acting as a nucleophile. You see? So I would want you to circle these things or box them where I'm asking you where they're acting like they're supposed to be acting. So, for example, there's an X over here, just like there's an H right there. I wouldn't call this H the electrophile. I'd call him the electrophile here because that's where he's acting as the electrophile. I wouldn't call this X a nucleophile over here, just like I wouldn't call him one over here. I call it where he's at, where I'm showing that that's what he's doing. He's being attracted to that positive carbonium ion. A nucleophile is attracted to positive things. An electrophile is attracted to negative things. That would be why the H would be. And finally, I could ask you, which of these is the slow step? And what would you say? Yeah, the first step is a slow step. And I would identify the first step as this step here. Okay, this is step 1. And this is step 2. And the first step is the slow step, and he alone determines the overall rate of the reaction. That step alone does that. That actually is kind of important in the future when we start. If you wanted to talk about, again, you're not going to be chemists most likely. You're not going to be working in that. But if I know that that's the slow step, everything I could do to make that step happen faster is everything I can do is what I want to do if I want to increase my yield and lower the amount of time I'm going to spend making this product. If I know that the second step happens really fast anyway, I'm not going to care about that. I'm going to care about making it easier for H to get together with those electrons over there. So what solvent I pick, what what bromine or chlorine? Is it bromine, chlorine, iodine, fluorine? Which something called a leaving? We're going to talk about this tomorrow. Which would be easier to break H away from? All of that is going to be more important. So if I want to use like HF versus HI, who do you think is going to be easier to get an H away from? HF or HI? HF or HI is going to, which one's going to be easier to pull an H away from? HF or HI? Think. Look on the periodic table. Which one will be easier to remove the H from? HI. Because F, fluorine, is certainly going to be hanging on to that H he's got. He's not going to want to lose him, right? Whereas the iodine won't hold as tightly. So there's knowing that this is the slow step, I would know that HI would be a better guy to use here than HF, right? All right, so that's the kind of stuff that understanding the mechanism helps us to understand why the reaction happens slower or faster. Okay? All right, good enough.